Everybody, that's great. Who of you have done lean metaphor coding? Okay, like gives me some understanding of the spectrum area. Who of you have used Haskell before? Okay, that's where you're coming from. That's great. Okay, so my talk is about recursive definition, just because. Oh, maybe I should talk first about why I'm here. I'm here because I like lean, and because I like lean, I got the opportunity to actually, or maybe I should closer to the laptop for the benefit of the remote participants. I actually have the privilege of being able to work on lean. So I've joined the Lean Pro. It's a nonprofit startup, strange thing. I can explain that later more if you want. And we develop lean, the core system, and I get to work there. That's great. And one of the things that I've mostly been working on the last year or so has been everything around recursive definitions. So I thought I'd give a talk about that. I think the agenda says it's live coding. We then agreed that I'll just do half an hour, then an hour. So I did the live coding, but I did it ahead of time. But it's still VS Code, so we can edit things. And it's gonna be the most fun the more you stop me and ask questions and send me off on tangents or even normals if you like. And I don't have that much material. I think but just run through it. We'll be through in 20 minutes. So feel free to stop me and ask questions and make this as interactive as you want it to be. And also we started early. So maybe, yeah, please do ask questions. we'll be through very quickly. It's good that plenty of you are coming from a background of, let's say, Haskell or probably any other programming language, because then you might be wondering, like, what's so interesting about recursive definitions? You just write a recursive function and that's fine, right? That's what you do when you're programming. Now in Lean, that's a bit more complicated for good reasons. So let's get started. So hot take, Lean does not have recursive definitions. Okay, you might be thinking that's strange because you've probably written a recursive function at some point already in your Lean life. But it's still a true statement if you consider Lean as the Lean logic. So remember that Lean is both a theory improver and a programming language. And I guess for the first 20 minutes of the talk, I'm going to talk about Lean as the theory improver, the system that allows you to make statements and then prove them in a logic. And the logic underlying Lean is based on type theory. And the particular variant chosen by Lean is one that does not have recursive definitions. We'll be talking a lot about the kernel of Lean. The kernel of Lean is the little piece of code, and it's really little compared in size of the rest of the Lean system, that is actually responsible for checking the proofs that you produce. You can think of it as a little black box. You feed it definitions, you feed it theorems, it says yay or nay. That's all it does. And it's kind of self-contained. It's very trustworthy that way. It doesn't change a lot. And everything else that Lean does is basically take what you write and prepare it for presentation for this little kernel component. It elaborates what you wrote because you don't want to write all the details. You want to use implicit arguments, you want to use tactics. And all this is handled by Lean, the wider system. But then what's being passed to the kernel is very, very explicit, very technical in a way. And this kernel itself, the core component for the logic of Lean, does not support recursive definitions. Now, I'm making a very didactic blunder here by starting with this code. Don't read this code. I'm going to just tell you what it does. I just want to demonstrate what happens if you try to pass something to the kernel that is recursive, just to prove the point that the kernel doesn't support recursion. Now, the whole system of Lean is trying to help you to not pass anything that's like invalid to the kernel. But usually you will never see the kernel complain because the system already tries to only pass things to the kernel that are correct. So I have to really try hard to bypass everything that Lean provides us, really go down to the raw interface of the kernel, which is like this add decal function down here, and pass a definition there. But I can do that. Lean is very extensible, very open. You can dabble with these things. So this code, without explaining the code, what it does, it creates the definition we see on line 17. It defines a function test that is defined to be test of n+1. You can write that in Haskell, not very useful, but the compiler will compile it, it will run it. It will run it for a long while, I guess, but it will run it. if I try to pass this to the lean kernel, and I can remove this, and so you see the red squiggly line and the cross mark and everything, and the info view, it says unknown constant test, which makes sense. The kernel that basically checks the right-hand side, the definition, the thing that we wrote here. Well, actually, we wrote it further down, but this is what we meant. And it tries to check it and finds, okay, there's a reference to a function called test, and it doesn't know test yet. It has to check the definition before it defines test, and it complains. Okay, so lean, the kernel, does not support recursive definitions. Why is this so important? This is so important because we want the lean kernel to be a sound type checker, sound logic. Sound meaning, well, you can only prove things that are true. And if that kernel would support arbitrary recursion without any particular additional protections, then that would immediately break the soundness. Because we could immediately define a theorem like, a definition like this, which I think would be really bad. So it's a theory, like it's a proof that any proposition is true, and the proof just refers to itself, circular reasoning, and recursion allows circular reasoning if you're not careful. And the easiest way of being careful about recursion is to forbid it, which is the choice taken by lean, the kernel. So there's a question.
Give us a bit of perspective. So lean doesn't support recursion for a good reason, but that is also true for many, if not all, other theory improvements, isn't it?
No. I mean, I hope I'm not wrong here, but as far as I remember, okay, it is true for Isabel, which is a bit further away in the family tree of theorem prover. The more closer related theorem provers like Koch and Acta, they do support recursion in the kernel, and they have code in the kernel to forbid this particular kind of recursion. So it's the guardedness checker, for example, and I don't know what they call it in Acta. So they allow recursive definitions, and then they apply certain checks to make sure that the recursion is okay, whatever that may mean. And in a way, this is maybe part of the reason why Leo called lean, because the kernel can be smaller if it doesn't have to, for example, worry about getting recursion right. So in the Koch, the kernel, it understands recursion, makes some things easier. There are certainly benefits to this design choice, but it means there's more complicated code inside the kernel that you have to trust. Whereas in lean, okay, no recursion makes things easier. Yeah.
What's the deeper reason? My course understanding is that the proof language is a language where every program terminates, right? Otherwise, the prover couldn't be able to check it, right? And as soon as you add recursion, you get the problems of bottoms and CPO and stuff like that.
So in Koch and Acta, as far as I can tell, and at least if you're not going to like co-recursion and things, it allows recursion, but only if it can see that the recursion is going to be terminating for precisely that reason. In Isabel, things are different because the logic doesn't actually compute. I think I would put this discussion further at the end of the talk. We'll talk a little bit about this on the way, and then it'll be easier for everybody to follow. But this is a discussion I very much enjoy having. Yeah, there's a question.
Confused by an example function, because if you want to evaluate at 1, you need to evaluate the function at 2, which is the function at 3, and so on. Shouldn't you define it the other way around if you want to have any hope of doing anything useful?
Who says I have any hope of doing anything useful here? I was trying to break the system. No, you're absolutely right. This is a pointless function that will just diverge and will not do anything useful. Just the simplest recursive function that I could. I mean, yeah, I guess I could do this, like write minus here and write not sub, probably same thing. But in fact, this doesn't terminate either, because then you've called test 0, and 0 minus 1 is obviously 0. No questions about that this is the correct answer for 0 minus 1. And then it just keeps calling test 0, so it doesn't change anything. I didn't want to go into like pattern matching here in this little example.
even without the non-direct?
Not directly.
Plus one is not well defined. So
Right. No. I mean, maybe this was a bad example. Something doesn't work. This doesn't work. The lean kernel rejects it on very basic grounds, like it's recursive. I don't want to see it. We will now see various ways of actually defining a recursive function as a user. And maybe you can, every time you see it, and think about, could I actually define this bad function with this way? And you will see that they almost all forbid that. There's an interesting. We're going to have an interesting discussion at slide 6. So to keep that in mind. Okay, so the lean kernel doesn't support recursion. But obviously, we want to write programs or define things that are conceptually recursive. So how does this work? The escape hatch that the compiler or the kernel provides us are called recursors. So usually, at least when we start, recursive definitions follow the structure of some inductive definition. Like, you define list as an inductive data type, and then you write a function that is defined by recursion over lists. Or as a simple example, and very typical for the thing we do in theorem proving, is we define the natural numbers as either 0 or the successor of a natural number. Who has seen this definition of natural numbers before? Great, good. This is good, because otherwise, yeah. So this is the actual definition from the standard library. I copied it out, put a namespace to avoid conflicts, but this is what it's done under the hood. And this creates in the kernel what's called a recursor. And if you squint at it, it's really just the principle of induction as you know it from high school or university or wherever. So in order to prove something or define something, the same thing here, define something for a natural number t, like a function of the natural number t, you say what to do for 0 and what to do for if it's a successor of a natural number. And in that case, you get the result of the previous number. We'll see it in practice in a moment, but really this is functional. This is natural induction, natural numbers. And this recursor is a definition. You can treat it like a function. You can call it, but it doesn't have a definition really. So if you check it, you get the type. So we just saw that. You can also print it, and it will say recursor. It's primitive. It's built into the kernel. The kernel gives you one of these every time you define an inductive data type. And this is our escape hatch. This is how we can define things that behave as if they were written recursively. So remember, one of the first functions you probably want to define on natural numbers is addition. So addition written recursively means we look at the first number. If it's 0, we return the second number. If it's a successor of a number, we recurse on the number it's a successor of, the a prime, and then add 1 at the end. This is something you would see in a tutorial on very basic functional programming and inductive data types. And obviously, or maybe not obviously, but it's not so hard to write this function using the netrec function. We say that we want to compute something non-dependent. So the result type doesn't depend on the argument. We want to compute something of type net. In the first, if it's a 0, the input, then we return b. If it's a successor, then we get the result of the recursor call, so to say, as an argument to this local function here, and then we just add 1. And you can see the similarity to the one above.
Just because I forgot the original definition, what is the type of underscore a quote?
It's net. Why don't I? Oh, I disabled hovers because they are very confusing during talks. Yeah, so it's basically the thing that the argument was a successor of. It's the a prime from above. So okay, and this is now a non-recursive definition. It's using the recursor, but there's no reference to add anywhere on the right-hand side. And this works. Yeah, next question, please.
It works because the add function at successor of n is not the same as the add function at n, right? So your you can structurally prove that you're not evaluating the function like the same argument, or you're not feeding the result back into the same thing.
Not sure. Can you rephrase? I'm not quite sure.
Well, the proof why this works is because you're like through the pattern matching, you're deconstructing the numbers. So other human improvers would say, yeah, okay, I have some trace or some proof that I'm reducing the argument, making the argument smaller, and therefore eventually has to.
But yeah, if it's quinteted, if you try to reproduce this in a different system where the recursive isn't primitive, then maybe that's what's happening. But here, we just get this net rec function. There's no proof around. And by construction, everything that I can define with this net rec recursor is fine. There's no additional requirements. Because, I mean, you're right in a way that, and we'll get to that next slide, the net rec recursor only allows me to define things following a certain pattern, very restricted pattern, only primitive recursion. But there's no more checking done. This is, everything I can define with this combinator is okay. And again, this makes the kernel lean because it doesn't have to do any side conditions on whether I'm using it in a good way. Okay, so this is how you define, no, I shouldn't say that. This is how one could define recursive functions for the lean kernel. Obviously, this is not the way you want to define recursive functions because it's quite tedious and hard to read. You really want to write something like this. And I guess that's one of the reasons why you have lean the system and not just lean the kernel, because lean the kernel would be quite tedious. And now we get to the things that are actually relevant for users, namely ways in which lean allows you to write something in a more high-level way, and then behind the scenes converts it in something that the kernel likes. And the first way of defining recursive functions in lean is, or maybe I should start with, I could have just written this definition that I had in a comment on the earlier slide as the thing I want to achieve. I can just write it, and lean will do the work for me. It will understand this recursive, this function definition, and transform it into something that is non-recursive and using recursor. We can actually have a peek at what's lean doing there. So if you look at print add and open the info view, we see that it's not the right definition that we gave. It's something relatively different. There's something, oh, there's a brec on. Didn't I just say we use the net rec? Okay, looks like lean is doing something more complicated than I just hinted at. But if we look at the net brec on definition, we see that that itself is defined with the net recursive. So I didn't lie. It's just that lean is doing more. I will not go into details what this brec on does and how it works. It's actually quite a neat trick. There's a paper on it you can read by Connor McBride, probably. Shouldn't say something while recorded if I'm not sure. But I want to show you why it's useful to not go directly to the net rec recursor. It's because it allows what's called cause of value recursion. So look at this very classic definition of a recursive function. It's the Fibonacci numbers. We first check if the number is 0 or if it's 1, and then we return something, or if it's the successor of the successor of a number, if it's n plus 2. And if it's n plus 2, then we have two recursive calls, one on n and one on n plus 1. And this is not a primitively recursive function in the sense that you can immediately squinted it and see what you have to pass to net.rec to make it work. There's a recursive call here, that's fine. That is a call on an immediate subcomponent of one of the parameters. N is a parameter, you pattern match, you get you get a successor constructor, and you do a recursive call on the thing directly. That's primitive, but there's also this call, and it's basically reaching 2 steps into the constructors. And that's not primitive recursion, but there's a construction that allows you to precisely do that. It's called cause of value recursion, and it means that in lean, structural recursion is not just immediate subcomponents of the constructor, but any subcomponent. I wouldn't say arbitral, well, any syntactically obvious subcomponent. Yes, please. I actually don't know which ones have something like that and which one don't, and which one need to encode it. Is it a question or a statement? Curiosity. I will, since it's recorded, I will not lean out of the window and say bad things about other systems. Wouldn't. You don't want to do the challenge yourself?
Like if you run print, I mean, is it the same?
Yes. It's the thing that brec does is precisely that. It allows you to brec basically it's like a recursor, but it gives you all previous values in a data structure called this net below thing on the right. So think of it as a memoization technique.
What does B stand for in brec?
Bounded, maybe. Actually, I don't know. Is it bounded? Bounded? No, but it's bounded recursion. I mean, it's called causal value. I don't know. Yeah, it would fill a whole talk to explain, I think, the construction underneath. So for now, I'll just stick with it allows you to do these things. Another thing that we added relatively recently is that you can also do mutual recursion in a structural way. So here we have two functions, they call each other. They're both structurally recursive, so even primitively so. But they call each other and then lean behind the scenes does some construction that like tuples that make like turns both functions into one function that is structurally recursive and unpacks them later. Sometimes convenient. Okay, so this is structural recursion. Any questions about structural recursion before we go to more interesting kinds of recursion? Perfect. The next one is well-founded recursion. So sometimes you want to define functions that are not structurally recursive, not even that like this causal value thing. And a typical, maybe a bit too simple even, but still a classic or typical example for that is if you do some kind of array processing and index calculations. So in this function, which checks whether all elements of an array are the same, we have an index I, and as we usually do, we increase the index in one step, every step. So there's nothing getting smaller at least among the parameters of the function. But it's still going to be terminating because we stop when we have reached the size of the array. And this is not structurally recursive. We could make it with some helper parameters and things, but that's not the point. We want to write this function. And Lean supports what's called well-founded recursion, which is a very powerful and flexible tool. But it's also more elaborate. You have to do more things. At least sometimes you have to do more things. So you have to provide two things in addition to function. You have to say, here is a measure. It's a function from the arguments, from the parameters of the function. So it's some expression involving I. Typically, it's of type net, not always. We'll get to that. And you basically say, here's something, and this measure gets smaller in every recursive call. And because natural numbers are bounded from below, that means if something gets strictly smaller in every call, eventually it has to hit 0 and has to stop. But you don't just have to say, hey, believe me, this gets smaller. You also have to prove it. So there are two things you have to provide. You have to provide the measure, and then you have to provide a proof. And if you look at the proof state here, we see, well, precisely that Lean is asking us to prove what we just claimed would be true. So we see on the left-hand side, well, on the right of this model, we see the measure, with I being the parameter. On the left, we see the measure again, but now with the arguments of the recursive call. We have I plus 1 here. If I would change this to I plus 2, then we would see I plus 2 here. We also see some things we can use in this proof. In particular, we can use that I is smaller than the array, which is the condition that the branch that we're in. So we can do the proof We have automation for natural numbers and integers with omega, so this takes care of it. Not much to do here in terms of proving. But conceptually, that's what we have to provide. This is a very powerful tool. There are many functions that are terminating that are not structurally recursive, where you will be able to give a termination proof that way. Define a measure, prove the things, and then you're done. That's fine. Lean is happy. Yeah.
Specify termination measure of the increasing and screwing explicitly, or can we even further?
Great question. Let me scroll down. In many cases, Lean will automatically infer the termination measure and or the termination proof to answer your question. So this is the same function definition. This was not prepared. Did you just ask that? No. But I mean, it was an obvious question at this point. Now, there are some heuristics in Lean trying to infer one or the other. It's actually, and this is something I built, so I'm somewhat proud of it. In this case, the termination measure is non-trivial. It's not just one of the parameters, but it still finds it. The trick is that it finds, oh, you compared the parameter, like there's a less than comparison somewhere in the context. Let's try the difference. It's a very effective thing for many cases. Yeah.
Because if you view it as a higher order function, so you fix the array, then you've got just a function that has enough argument. And you can see in the body that it's calling. No, okay, I put one, so you have to sort of invert it with the. Okay, no, it's not true. I think it's that.
Right. If you,
but you can analyze a function that has just a natural number argument.
But you still have to find the function. Yeah. So indeed, if you think this was trivial and you want to check, you can use termination by. And it will tell you what it actually inferred as a termination measure, and maybe you're surprised about what it finds. Yep.
If you get rid of the dependent if, does it fail?
It does not. It fails here because the array indexing needs it. I can make this, don't bother with me. It still finds this. And if you look at the decreasing by proof, we see it actually inserted it again. So for the purpose of termination proofs, it will turn every non-dependent if then else into dependent if then else. That's a little convenience. But good question. Okay. One more thing about well-founded recursion. It doesn't have to be just net the measure. It could be something more complicated as long as it has a well-founded relation associated with it. I'll skip explaining what it means, but one good example is you can have something like, oh, I have two measures, and either the first one gets smaller, or the first one stays the same and the second one gets smaller. That is, you can't express this in one measure, at least not in one net valued measure, but it's still valid for termination proof. And this is actually something you will use for this infamous Ackermann function. And we can see that Lean here also has inferred the termination by, I can actually insert it. How do I actually? Yeah, insert this as the termination measure. Now you might be wondering, if well-founded recursion is so great and things can be automatic and it's so much more powerful, why even bother with structural recursion? And there are basically two main reasons why structural recursion is still very useful. So first, you don't need to give a proof, just less work. And maybe for complicated things, Lean will, I don't know if Lean will always find a well-founded termination proof in all the cases where structural recursion could work. But there's just no proof. Like even, yeah, Lean doesn't have to calculate some proof. It may be faster. The other bigger one is good kernel reduction behavior. And this, I think, touches on a point that Olaf brought up. There are sometimes the kernel has to actually evaluate a function. This can happen if a function appears in a type and you want to do type checking. Then you need to find out if you know, like a vector of length n+1 is actually equal to some same type as some other vector. And the kernel will be able to reduce functions defined by structural recursion. It will not be able to reduce functions defined by well-founded recursion. So if the thing you're defining is in any way relevant for kernel reduction, it's in a type, more advanced topics, but maybe you want to use it in a proof by reflection proof, interesting proof technique, then yes, avoid well-founded recursion or you'll have problems. 5 more minutes, which, yeah, that's fine. I'll do the next one. Okay, this is now very cool and maybe confusing after everything I talked about. It's also very new. We just added it last release or so. A new way of defining recursive functions called partial fixed point. And here, there's no termination proof. And the functions don't even have to be terminating, which sounds confusing after all I said before. Let me first give an example. So here's an example. It's the famous McCarthy F91 function. It's defined purely to make termination proofs hard. The thing is, it calls itself and then takes the result and passes the result to itself again. And in order to prove that this function is terminating, it is terminating on all inputs. To prove that it's terminating, you basically have to first prove a little bit about the function you're about to define, and then use the proof in the termination proof. You can do that in Lean with well-founded termination, but you have to change the type to use subtypes, very complicated. With partial fixed point, you can just define it. Now it's defined. Now you can prove some things about it, some helper lemmas, and then you can maybe prove that it's total. There are some rules when this actually works. It doesn't work for all functions. And I'll focus on the main use case, or maybe the simplest one. It has to be a function returning an option. That's a plain option data type from the library. The conceptual idea is that as far as the kernel is concerned, if this is not terminating, it will have the logical value of none. Yeah, this takes a while to settle. Yeah, but that makes it fine. That makes it a total function from the point of view of the kernel. And this works if the function type is option and you don't look into the option. So you only use the bind operators. This means that once something is none, it stays none. This is the crucial property here. Since we're getting close on time, I will just leave it like this. I want to. You can also. No, wait. We had this one question. I want to do this. We can actually define this function using partial fixed point as well. Why is it complaining? And it gets accepted. I will not explain what that means. That's something for the break. It's correct. It's not useful. Let's put it this way. The F91 on Zulip, I expanded a little bit on this example. You can see how you can then use this definition in proofs. And then for the last 2 minutes, I will briefly explain something about compiler versus kernel. So we've talked about the kernel exclusively right now, everything about theorem proving. Lean is also it's also a programming language that you can use to write normal programs. And the Lean, the system, basically takes your things, it does your definition, it elaborates them, and then it splits the path. One direction goes in the kernel, and the other direction goes to the compiler and does normal functional programming compiler stuff. And everything you saw so far, this translation, this termination checking, only affects the path towards the kernel. The compiler sees the definition before recursion is removed. So all these 3 definitions, this is addition defined with in a different type, defined using the 3 ways of defining recursive function we just saw, are identical to the kernel. Identical to the compiler. They're compiled just the same. And sometimes you don't care about the kernel. You only want the compiler to look at your definition because you're just writing a normal program. Lean itself is written in Lean. We don't want to verify Lean for the foreseeable future. So we just say, okay, this is just for the compiler. You can use the partial keyword that allows you to do any kind of recursion, just like in Haskell, in a way. It still exists to the kernel as a definition, but it doesn't have any content. It's an opaque definition. And then there's even the even harsher unsafe. This means this definition doesn't even exist as far as the kernel is concerned. And yeah, I want to say that partial is not infectious. So you can define a partial function, you can call it from other functions. The other functions you will not see that they're calling partial functions. It is not the case that any program you write in Lean is automatically guaranteed to be terminating as a compiled program. This is sometimes a misconception that I want to clear up. It may be that you're calling a partial function that diverges just fine. You will not see this in the types or in the annotations. Unsafe is infectious, so you can only call unsafe functions from unsafe functions, but there's an escape hatch. And that brings me to the end of the things I have prepared. I think we have plenty of questions for the coffee breaks then. And with that, I want to thank you for your attention.
Yeah, this is great stuff. We really kind of went all the way to the edge of the time. I'm looking forward to discussion, coffee break, and afterwards. But we have another speaker. Leo, brings it. Yeah, please.